Look up at the night sky on a clear, dark evening. What you see is a canvas of peaceful, twinkling lights, a picture of cosmic serenity that has inspired humanity for millennia. But that tranquility is an illusion, a beautiful lie. The true nature of the universe is one of unimaginable violence and raw, explosive power, where events unfold on a scale so vast they can rip apart the fabric of space-time itself. We are about to journey into the heart of these cosmic cataclysms, to witness the birth and death of stars in the most energetic explosions the cosmos has to offer. These are not just distant curiosities, they are the fundamental forces that have shaped everything we are and everything we see, from the atoms in our bodies to the very elements that make up our world. This is a story of ultimate power, written in fire across the emptiness of space. Get ready to have your perception of reality fundamentally altered as we explore 30 incredible facts about the universe's most energetic explosions. We will venture beyond the familiar sparkle of a supernova into realms of energy so intense they defy easy comprehension. We will confront cosmic phenomena that release more energy in a few seconds than our sun will emit over its entire 10 billion-year lifetime. These are the events that light up the darkness, that forge new elements, and that ultimately make life possible. This exploration is not just a catalogue of astronomical wonders. It is a journey to the very limits of physics, to the edge of what we can possibly understand. Each fact is a piece of a larger puzzle, a glimpse into the chaotic, beautiful, and terrifying engine that drives our universe forward. So, let's begin our countdown, starting with a phenomenon so brilliant it can outshine an entire galaxy. To even begin discussing these events, we first need to understand what we mean by an energetic explosion in the cosmic sense. We're not talking about firecrackers or even the most powerful nuclear weapon humanity has ever devised. Those are barely whispers in a silent room compared to the cosmic detonations we're exploring. An energetic cosmic explosion is a fundamental release of energy on a scale that challenges our very comprehension, an event where the laws of physics are pushed to their absolute limits. These are violent, sudden, and transformative events that can tear apart stars, light up the darkness between galaxies, and forge the very building blocks of planets and life. The key to grasping their immense power lies in a single, staggering comparison: our Sun. Our star is a colossal nuclear furnace, fusing over 600 million tons of hydrogen into helium every single second. It has been doing this for nearly 5 billion years and will continue for another 5 billion. The total amount of energy it will release over its entire 10 billion-year lifespan is a number so large it's almost meaningless. Yet, in a cosmic explosion, that same incomprehensible amount of energy can be released in a flash, sometimes in just a few seconds, a minute, or a handful of hours. It is an almost instantaneous expenditure of a star's lifetime worth of power. This isn't just a difference in degree, it's a difference in kind. It's the difference between a gentle campfire that warms you through the night and the entire forest erupting into a firestorm in the blink of an eye. This unimaginable energy release is what powers the brilliant flashes we can see from billions of light years away. And it's this raw, unfiltered power that we will be measuring and marveling at as we count down through these 30 facts. That beautiful illusion of a peaceful cosmos is shattered by the death of a single star. Picture a star not like our stable sun, but a true titan of the cosmos, a star many times more massive. For millions of years, it has burned brilliantly, fusing lighter elements into heavier ones in its core, much like a layered cosmic onion. Hydrogen fuses into helium, helium into carbon, and so on, all the way up to iron. But here is the critical turning point. Creating iron requires energy instead of releasing it. For the star, this is a catastrophic bill coming due. The star's core, which had been held up for its entire life by the outward pressure of nuclear fusion, suddenly loses its power source. With the fusion furnace shutting down, there is nothing left to fight the relentless, crushing force of the star's own immense gravity. In less than a single second, a core that was once the size of Earth collapses inward, plummeting at speeds reaching 70,000 kilometers per second. Matter is compressed to such an insane density that protons and electrons are forced together, merging to form neutrons and releasing a flood of ghostly particles called neutrinos. The core becomes an impossibly dense sphere of neutrons, a city-sized object containing the mass of 1.5 suns. When this newborn neutron star can be compressed no further, the inward-falling material from the outer layers of the star slams into it with unimaginable force. This collision creates a rebounding shockwave, a cosmic sonic boom of epic proportions. At the same moment, the incredible flood of neutrinos, carrying away the vast majority of the explosion's energy, injects even more power into this shockwave. The result is a cataclysmic rebound. The outer layers of the star are blasted outward in one of the most violent events since the Big Bang itself. This is a core collapse supernova. For a brief, spectacular period, this single dying star can outshine the combined light of every other star in its entire host galaxy. Its brilliance is so intense that it can be seen from halfway across the observable universe. But the legacy of a supernova is far more than just a spectacular light show. In its seething, expanding debris cloud, temperatures and pressures reach levels impossible to replicate anywhere else. It is within these expanding shells of stellar material that the universe forges the elements essential for life as we know it. The gold in a wedding ring, the oxygen we breathe, the calcium in our bones. Nearly every atom in our bodies heavier than helium was forged in the heart of a massive star and then scattered across the cosmos by a supernova explosion. We are quite literally made of stardust, the remnants of cosmic catastrophes that occurred billions of years ago. This explosive death is not an end. It is a necessary act of cosmic recycling, seeding the galaxy with the raw materials for new stars, new planets, and ultimately new life. Just when you think you've grasped the ultimate limits of cosmic violence, the universe reveals an even more extreme class of explosion. If a supernova is a stellar cataclysm, then a hypernova is an apocalypse on an entirely different scale. These are the true titans of stellar death, events so immensely powerful they make a standard supernova look almost modest by comparison. The key distinction lies in the engine of destruction and the ultimate fate of the star. While a regular core collapse supernova leaves behind a dense neutron star, a hypernova occurs when the stellar progenitor is so incredibly massive and its core so unimaginably heavy that not even the formation of a neutron star can halt the gravitational collapse. There is no rebound, no second chance. Instead, the entire core of the star plunges inexorably inward, bypassing the neutron star phase completely and collapsing directly into a black hole. This is the heart of the collapsar model. The word itself, a portmanteau of collapsing and star, perfectly captures the sheer, uncompromising finality of the process. But the raw collapse is only part of the story. For this event to become a hypernova and produce its most famous signature, the star must be spinning and spinning very, very fast. Think of an ice skater pulling their arms in to spin faster. Now, imagine a star the size of our solar system doing the same thing as its core collapses. This rapid rotation focuses the collapsing material into an incredibly dense, rotating disk of superheated gas and plasma swirling around the newborn black hole, an accretion disk. It is from the furious poles of this system, perpendicular to the disk, that the universe unleashes its most focused torrent of energy. The infalling material, combined with the intense magnetic fields, gets channeled into two narrow, opposing jets that scream outward at velocities approaching 99.9% the speed of light. These are not gentle streams of gas, they are blisteringly hot, pencil-thin beams of pure radiation and atomic particles. If one of these jets is pointed fortuitously in the direction of Earth, we witness it as a long-duration gamma-ray burst, a flash of the highest energy light in the universe that can last from a couple of seconds to several minutes, outshining for that brief moment every other gamma-ray source in the cosmos combined. The broad, spherical explosion of the hypernova itself provides the sustained, brilliant visible light, while the jets provide the initial, unimaginably intense spear of gamma rays. The total energy budget of a single hypernova event is almost beyond calculation, often releasing more energy in a few seconds than our Sun will over its entire 10 billion-year lifespan. These are the true foundries of the heaviest elements in the universe, like gold and platinum, created not in the relative calm of a supernova, but in the chaotic, jet-driven maelstrom of a collapsar. And if the energy of a hypernova seems incomprehensible, prepare to be astonished by its most extreme and focused signature. We now arrive at a phenomenon so powerful it represents the single most energetic explosion known to occur in the universe since the Big Bang itself, the gamma-ray burst. To call these events powerful would be a profound understatement. A typical gamma-ray burst will release more energy in a mere handful of seconds than our Sun will radiate across its entire 10 billion-year lifespan from birth to death. This energy is not released as a gentle glow or a broad flash. It is concentrated into the most energetic form of light in the electromagnetic spectrum, gamma rays. For that brief moment, a single gamma-ray burst can outshine every other gamma-ray source in the entire cosmos combined, a beacon of pure, raw power visible from the very edge of the observable universe. The discovery of these events is a story of Cold War intrigue. In the late 1960s, American military satellites named Vela were launched to monitor the globe for secret nuclear weapons tests, which produced telltale gamma-ray signatures. What these satellites detected, however, were not earthly explosions, but brief, intense flashes of gamma rays coming from deep space. The data was classified for years as scientists worked to rule out a Soviet origin. Once declassified and studied, the scientific community was left utterly baffled. The origin of these colossal blasts was a complete mystery for decades, and solving it required understanding that not all gamma-ray bursts are created equal. Astronomers eventually realized they could be sorted into two distinct families based on the duration of their gamma-ray emission, long bursts and short bursts. This simple distinction, based on a time measurement, became the master key that unlocked the secrets of their violent origins. A long gamma-ray burst lasts anywhere from 2 seconds to several minutes. These are the events directly linked to the hypernova we just explored, the death cries of rapidly spinning, massive stars as they collapse into black holes and launch their universe-piercing jets. If one of those jets is pointed like a cosmic rifle directly at our solar system, we register it as a long-duration burst. The shorter class of bursts, lasting less than 2 seconds and often just a few tenths of a second, tells a different but equally dramatic story of destruction. These brief flashes are thought to be the result of a different kind of stellar cataclysm involving the densest objects in the universe, neutron stars. Imagine a binary system where two ultra-dense neutron stars are locked in a gravitational dance, slowly spiraling inward over millions of years as they lose energy in the form of gravitational waves. Their final moments are one of the most violent events imaginable. They don't just bump into each other, they tear each other apart in a cataclysmic collision, creating a black hole almost instantaneously, and in the process launching their own incredibly powerful ultra-fast jets. The merger of these two stellar corpses also flings out a cloud of hot, neutron-rich material, forging immense quantities of the universe's heaviest elements like gold and platinum in a single, brilliant flash. So, whether it's the collapse of a single stellar giant or the catastrophic merger of two dead stars, a gamma-ray burst serves as the universe's definitive announcement of a black hole's birth, an event of such pure, concentrated fury that it briefly dominates the entire high-energy sky. This simple time-based classification, long versus short, is one of the most elegant and powerful tools in an astronomer's kit, acting as a cosmic pedigree that traces two completely different paths of destruction. A long gamma-ray burst shining for more than 2 seconds is fundamentally the death scream of a truly massive star. But it's not just any star, it's a specific type of stellar giant, one that is not only enormous but also rapidly rotating and relatively poor in heavier elements, often found in active star-forming regions of galaxies. These specific conditions are crucial because they allow the star to maintain its angular momentum as its core collapses. It's this rapid spin that powers the central engine, forming the accretion disk and focusing the explosive energy into those thin, relativistic jets that can punch their way out of the stellar envelope. When we detect a long burst, we are witnessing the final public announcement of a black hole's birth, an event that began with the core collapse of a star dozens of times more massive than our Sun. The initial flash of gamma rays comes directly from within these jets, and as the jet plows into the surrounding interstellar material, it creates a sustained afterglow visible across other wavelengths, from X-rays to radio waves that can be studied for weeks or even months. This afterglow is the crime scene investigation, allowing astronomers to pinpoint the burst's home galaxy and confirm its association with a recent supernova-like explosion. In contrast, a short gamma-ray burst, lasting less than 2 seconds and often just a few milliseconds, tells a far more compact and equally violent story. These events are the final, furious moments in the life of a binary system consisting of 2 neutron stars, or potentially a neutron star and a black hole. For hundreds of millions of years, these ultra-dense stellar corpses have been orbiting each other, gradually losing orbital energy by rippling spacetime itself, emitting gravitational waves. This slow, cosmic dance of death causes their orbits to tighten inexorably until, in the last fraction of a second, they spiral inward at a significant fraction of the speed of light and collide. The merger creates a black hole almost instantaneously, and the incredibly strong magnetic fields and gravitational forces can launch a similarly focused jet, but one that is much briefer and emerges from a far more compact environment than a massive star. Because there is no massive stellar envelope to break through, the jet can escape almost immediately, resulting in that characteristically short, hard spike of gamma rays. The aftermath of a neutron-star merger is just as scientifically rich, serving as the universe's primary forge for the heaviest elements like gold, platinum, and uranium. So, this simple 2-second rule does more than just sort events into bins. It deciphers the very origin story of the explosion, telling us whether we are observing the death of a single colossal star or the spectacular collision of 2 long-dead stellar remnants. That initial blinding flash of gamma rays is just the opening act. It's the universe's sudden shout for attention, a signal that something profoundly violent has just happened. But it fades in seconds or minutes, leaving astronomers with a critical question. Where did that come from? The true detective work, the part that unravels the entire mystery, begins with what comes next: the afterglow. Think of it like this: if the gamma-ray burst itself is the brilliant muzzle flash of a cosmic cannon, then the afterglow is the lingering, expanding smoke cloud, glowing from the heat of the explosion and allowing us to trace the shot back to its source. This afterglow is a multi-wavelength phenomenon, a fading ember that radiates across the entire electromagnetic spectrum, from high-energy X-rays down through visible light and into the radio waves. As the relativistic jet from the burst plows into the surrounding interstellar gas and dust at nearly the speed of light, it creates a rapidly expanding shockwave. This shockwave acts like a colossal natural particle accelerator, energizing electrons to incredible speeds and causing them to spiral around magnetic field lines, emitting a broad spectrum of radiation as they do. This process, known as synchrotron radiation, is what powers the long-lasting afterglow. the X-ray component of the afterglow is usually the first to be detected after the initial gamma-ray pulse fades. It's incredibly valuable because it's bright and can be quickly pinpointed by space-based telescopes like Swift or Chandra, giving astronomers a precise set of celestial coordinates within minutes of the burst. This rapid localization is the starting pistol for a global astronomical campaign. Once they have the coordinates, ground-based telescopes all over the world swivel to that patch of sky, searching for the optical counterpart, the visible light from the afterglow. Catching this fading star-like point of light is a race against time, as it can dim by a factor of 100 or 1,000 in just a few hours. Successfully identifying it allows for a deep and crucial measurement, a redshift. By splitting the afterglow's light into a spectrum, astronomers can see how much the light has been stretched by the expansion of the universe, which directly tells them the burst's mind-boggling distance. This is how we know that many gamma-ray bursts are truly cosmological, occurring in galaxies billions of light-years away. Finally, as the expanding shockwave continues to decelerate and interact with more material, it begins to emit strongly at radio wavelengths. Radio telescopes can monitor the afterglow for weeks or even months, long after the visible light has faded to invisibility. This radio data provides a unique window into the total energy of the explosion, the density of the surrounding environment, and the geometry of the jet itself. It was the systematic study of these multi-wavelength afterglows, a capability that only became routine in the late 1990s, that finally solved the long-standing mystery of what gamma-ray bursts truly are. By tracing the afterglow back to its host galaxy, astronomers confirmed that long bursts are indeed linked to star-forming regions in distant, often faint galaxies, directly connecting them to the deaths of massive stars. Without the vital clues provided by the afterglow, a gamma-ray burst would just be a fleeting, untraceable flash in the cosmic dark, a mystery without a solution. While the collision of neutron stars produces the short gamma-ray bursts we've discussed, the light show is far from over. The real cosmic alchemy begins in the aftermath of that initial, furious merger in an event known as a kilonova. The name itself provides a clue to its immense power, kilo meaning 1,000, as these explosions can be roughly 1,000 times brighter than a classical nova, though still not as luminous as a full supernova. But what a kilonova lacks in raw brilliance, it more than makes up for in its role as the universe's ultimate goldsmith. For decades, scientists were puzzled about the origin of the heaviest elements in the periodic table. We knew that regular supernova could forge elements up to iron, but the process for creating things like gold, platinum, and uranium remained a mystery. The answer was found in the chaotic debris of a neutron star collision. When two of these incredibly dense objects spiral together and merge, they don't just create a black hole, they also tear each other apart, flinging a small but significant fraction of their material, often several times the mass of our entire planet, out into space at velocities approaching the speed of light. This ejected material is an astronomer's dream laboratory, a soup of free neutrons so dense it's unlike anything else in the universe. It is within this expanding cloud that a phenomenal process called the rapid neutron capture process, or the R process, occurs. In the heart of a massive star, elements are built slowly, one proton at a time. But here, the conditions are so extreme that atomic nuclei are bombarded by a blizzard of neutrons, allowing them to capture multiple neutrons in the blink of an eye before they have a chance to radioactively decay. This rapid assembly builds up the atomic weight at an astonishing rate, climbing the periodic table in seconds to form the very heaviest and most stable elements. The radioactive decay of these newly forged, unstable heavy elements is what powers the kilonova's characteristic glow. It's a slow, hot simmer rather than a flash, causing the explosion to shine with a distinctive reddish light for several days before fading. The confirmation of this theory was one of the most celebrated moments in modern astronomy. In August of 2017, gravitational wave observatories detected ripples in spacetime from a neutron star merger labeled GW170817. Within seconds, space telescopes pinpointed a corresponding gamma-ray burst, and then ground-based observatories raced to find the source. What they saw was the first ever observed kilonova, its light slowly changing color and intensity exactly as models predicted. Most spectacularly, subsequent analysis of its spectrum revealed the unmistakable fingerprints of heavy elements like gold and platinum being created in real time. The calculations from that single event were staggering. The merger likely produced an amount of gold with a mass several hundred times that of the entire Earth. So the next time you hold a piece of gold jewelry, consider its incredible journey. It was not born in the heart of a stable star, but forged in the violent, universe-shaking collision of two dead stellar cores, a cataclysm so powerful it literally sprinkled the cosmos with the seeds of precious metals. The theoretical prediction of kilonovae was one thing, but actually catching one in the act required a level of cosmic coordination that seemed almost impossible. That all changed on August 17, 2017, an ordinary day that would become a landmark in the history of science. It was on that day that the LIGO Observatory in the United States and the Virgo Observatory in Italy detected a very specific ripple in spacetime. This wasn't the familiar signature of two black holes merging. The signal, named GW170817, was longer and lower in frequency, perfectly matching what astrophysicists had predicted for the final death spiral of two neutron stars. For the first time, we had heard the universe's soundtrack to a collision of stellar corpses, but the story was only half told. Mere seconds after the gravitational wave signal peaked, NASA Fermi Gamma-Ray Space Telescope and independently the European Integral Telescope detected a short, weak burst of gamma rays coming from the same general area of the sky. This was the moment the entire astronomical community had been waiting for. The gravitational wave signal provided a rough map of the sky, and the gamma-ray burst detection narrowed it down further. An urgent alert was sent out to astronomers worldwide, triggering the largest target of opportunity observation campaign in history. Telescopes of every kind on Earth and in space swiveled to search a vast swath of the southern sky. The race was on to find the visible light counterpart. Just 11 hours after the initial detection, optical telescopes in Chile began reporting the discovery of a new, faint point of light in the galaxy NGC 5933, located about 130 million light-years away. This was not a distant, fuzzy blob. This was a relatively nearby event happening in a galaxy we could study in detail. Over the following hours and days, that single point of light began to do something extraordinary. It faded in blue light but grew brighter in the infrared, evolving through a spectacular palette of colors from a hot blue to a deep cosmic red. This was the kilonova, unfolding in real time and in stunning agreement with theoretical models. The red glow was the telltale sign of the R process in action, the radioactive decay of newly forged heavy elements like lanthanides, which absorb blue light and re-emit it as red. For the first time, we weren't just theorizing about the origin of heavy elements, we were watching them be forged in a cosmic cauldron. Spectroscopic observations confirmed the presence of cesium and tellurium in the expanding debris, the direct fingerprints of the rapid neutron capture process. The data suggested this single event created an amount of gold and platinum with a mass many times that of our entire planet, scattering these precious metals across its host galaxy. The observation of GW170817 was far more than just a confirmation of a single theory. It marked the explosive birth of a new way of doing astronomy, multi-messenger astronomy. For centuries, we had studied the universe using only light, the electromagnetic messenger. Now, we could combine that with the gravitational messenger, ripples in the fabric of space-time itself. It was like being deaf and suddenly gaining the ability to hear, allowing us to experience a cosmic event in a completely new dimension. This single event confirmed the origin of short gamma-ray bursts, proved that neutron star mergers are the primary source of the universe's heaviest elements, and provided a new, independent way to measure the expansion rate of the universe. It was a transformative moment that connected fundamental physics on the smallest scales to the largest structures in the cosmos, all witnessed through the combined power of sight and sound. But the destructive power of black holes isn't only demonstrated in the mergers of dead stars or the collapse of massive ones. There is another, more direct and almost theatrical form of cosmic demolition, an event where a black hole actively tears a star to shreds right before our telescopes. We call this a tidal disruption event, and it is one of the most violent and spectacular displays a supermassive black hole can put on. Imagine a star, much like our own Sun, going about its normal orbit in the crowded core of its home galaxy. Through a simple gravitational misstep, its path brings it dangerously close to the galaxy's central, supermassive black hole, an object weighing millions or even billions of times the mass of our Sun. As the star approaches, it begins to experience a force gradient so extreme it defies earthly analogy. The side of the star facing the black hole feels a vastly stronger gravitational pull than the side facing away. This difference in force, the tidal force, stretches the star horribly, first into a football shape and then, past a critical boundary known as the Roche limit. It overcomes the star's own gravity, the force that has held it together for millions of years. The star is not swallowed whole. Instead, it is spaghettified, pulled apart into a long, thin stream of superheated gas in a process that can take just a few hours. Roughly half of this stellar debris is flung outwards at incredible speeds, ejected from the system entirely. The other half becomes bound to the black hole, forming a vast, swirling and turbulent accretion disk around it. It is the friction and immense pressures within this newly formed disk of what was once a star that heats the material to millions of degrees, causing it to glow brilliantly across the electromagnetic spectrum, from X-rays to visible light. This produces a sudden, bright flare that can outshine every star in its host galaxy combined for a period of months or even years. The light curve of a tidal disruption event is its own unique signature, rising rapidly as the accretion disk forms and then slowly fading over time as the stellar material is consumed or blown away. For astronomers, these events are like a controlled laboratory experiment on a galactic scale. By analyzing the light from these flares, they can measure the mass of the otherwise invisible supermassive black hole and study the physics of accretion in real time, observing how a monster lurking in the dark heart of a galaxy suddenly announces its presence by ripping apart a passing sun. Now, let's scale up the violence to a truly galactic level, moving from the death of stars to the awakening of monsters. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational sinkhole with the mass of millions or even billions of suns compressed into a single point. For most of its life, a galaxy's central black hole may be quiet, a dormant giant starved of fuel. But when a vast reservoir of gas and dust, or even an entire star, falls into its clutches, the black hole can erupt in an outpouring of energy so immense it redefines the word explosion. This is the engine of an active galactic nucleus, and the most extreme and luminous version of this phenomenon is known as a quasar. The name itself comes from quasi-stellar radio source because when they were first discovered in the 1950s and 60s, they appeared as star-like points of light in optical telescopes, yet they emitted powerful radio waves. They looked like stars, but they clearly were not stars. The true nature of these enigmatic objects was one of the great astronomical puzzles of the 20th century. The key to their unbelievable power lies in the process of accretion. As colossal amounts of material spiral inward toward the supermassive black hole, it doesn't fall straight in. Instead, it forms a vast, whirling disk of superheated gas and plasma, an accretion disk that can span the entire inner solar system. The friction and gravitational stresses within this disk heat it to temperatures of millions of degrees, causing it to glow with the blinding intensity of trillions of suns across the electromagnetic spectrum. It is the conversion of gravitational energy into radiation through this process that makes a quasar shine. In fact, the accretion disk of a typical quasar is so phenomenally efficient at turning matter into energy that it can outshine its entire host galaxy of hundreds of billions of stars. This is a single light source, a pinprick at the galaxy's core, that competes with the combined output of every star around it, but the raw luminosity is only part of the story. The most energetic quasars also launch jets of charged particles from their poles, beams that are accelerated by the black hole's intense magnetic fields to velocities so close to the speed of light that they are considered relativistic. These jets can extend for hundreds of thousands of light years, far beyond the confines of their host galaxy, punching into intergalactic space. When one of these jets is aimed almost directly at Earth, we see an even more intense and variable object known as a blazar, where the jet's radiation dominates everything else we can detect. The sheer power involved is staggering. A single quasar can be thousands of times more luminous than our entire Milky Way galaxy, and that energy is all being generated from a region of space not much larger than our solar system. This concentration of power is almost incomprehensible. We are essentially seeing the gravitational fury of a supermassive black hole converting entire suns' worth of mass into pure light and kinetic energy on a daily basis. These are not brief explosions like gamma-ray bursts. They are sustained outbursts that can last for millions of years, a continuous, universe-shaping eruption that dwarfs any stellar cataclysm. But to truly appreciate the raw power of these galactic engines, we need to consider the perspective from which we view them. Most active galaxies present themselves to us at various angles, allowing us to study their brilliant accretion disks and the structure of their colossal jets from the side. However, nature occasionally provides us with a front-row seat to the most extreme and violent spectacle imaginable. When the relativistic jet from an active supermassive black hole is aimed by pure cosmic chance almost directly at our line of sight, we are no longer looking at a standard quasar. We are witnessing a blazar, and the observational effect is nothing short of breathtaking. The term blazar itself is a blend of Bl-Lacertae object named after the first identified prototype and quasar, and it describes the most intense class of active galactic nuclei. The key difference is all in the angle. A jet that is pointed directly at us presents a unique set of physical conditions that dramatically amplifies its apparent brightness and alters its behavior. This phenomenon is due to a principle in special relativity known as relativistic beaming. As the material in the jet travels toward us at velocities exceeding 99.9% of the speed of light, the radiation it emits becomes heavily concentrated in the direction of its motion. It's analogous to the sonic boom of a jet fighter, where sound waves pile up as the plane approaches the speed of sound, creating an intense shock wave. In the case of a blazar, it is the light itself that gets piled up and focused into a brilliant, narrow beam aimed right at Earth. This relativistic focusing has two major consequences. First, it makes the jet appear phenomenally brighter than it would from any other angle, often outshining the entire emission from the rest of the active galaxy, including the accretion disk. Second, it causes the observed light to be strongly polarized and to span the entire electromagnetic spectrum with incredible intensity, from low-energy radio waves all the way up to the most energetic gamma rays. This makes blazars the most persistently luminous sources in the high-energy sky, dominating the extragalactic gamma-ray background. Their emission is also notoriously variable, flickering and flaring on timescales that can be as short as minutes. This rapid variability provides a crucial clue about the size of the region generating this immense power. For an object to change its brightness across the entire universe in just a few minutes, the emission must be originating from an incredibly compact volume, often no larger than our own solar system. This confines the engine of a blazar to the innermost, most violent regions immediately surrounding the supermassive black hole, where magnetic fields are trillions of times stronger than Earth's, and processes we can only theorize about are channeling the gravitational energy of infalling matter into these universe-spanning beams of pure power. While the violence of a supernova is brief, the remnant it leaves behind can be a source of unimaginable power in its own right. We've already met the neutron star, the incredibly dense city-sized core of a dead star. But among these stellar corpses, there exists an even more extreme and terrifying variant, the magnetar. If a typical neutron star is a cosmic cannonball, a magnetar is that same cannonball forged into the universe's most powerful electromagnet. To grasp the scale of its magnetic field, consider this. The Earth's magnetic field is strong enough to make a compass needle point north. A strong refrigerator magnet has a field of about 100 Gauss. The magnetic field at the surface of a typical neutron star is an already staggering 1 trillion Gauss, but a magnetar, its field is 1,000 times stronger than that, reaching an almost mythical 1,000 trillion Gauss. This is a level of magnetism so intense that it fundamentally alters the fabric of empty space around it. In a zone several hundred miles from the magnetar, the magnetic field is so powerful it becomes toxic to life as we know it. It would not just erase the data on every credit card on Earth. It would literally strip the atoms right out of your body from a distance greater than that between the Earth and the Moon. The atomic structure itself is warped, stretched into long, thin cylinders by the overwhelming magnetic force. These monsters are not born from ordinary supernova. They are thought to be the product of a specific, chaotic kind of stellar death, where the core of the progenitor star is spinning at an incredible rate, completing a full rotation in just a few milliseconds at the moment of collapse. This rapid spin, combined with the complex physics of the hot, newborn neutron star, acts like a dynamo, amplifying a pre-existing magnetic field to these ludicrous levels. A magnetar is essentially a universe-sized electric generator that was turned on at the moment of its own violent birth. And this stored magnetic energy doesn't just sit there, it has dramatic and violent ways of announcing its presence to the cosmos. The incredible external magnetic field exerts immense stress on the magnetar's own solid crust, a crust that is 10 billion times stronger than steel. This stress is not constant. The magnetic field lines frozen into the neutron star's structure are constantly tangling and shifting, putting unbelievable strain on the crust. Eventually, something has to give. The crust will fracture suddenly and catastrophically in a cosmic earthquake of epic proportions, a starquake. The energy released in this single event is staggering. In a fraction of a second, a starquake can release more energy than our Sun emits over 150,000 years. This sudden rearrangement of the crust causes the magnetic field to reconfigure itself, unleashing a torrent of radiation, primarily in the form of X-rays and gamma rays, in what is known as a giant flare. We have witnessed these events from our vantage point on Earth. On December 27, 2004, a magnetar located 50,000 light-years away in the constellation Sagittarius experienced a starquake so powerful that its gamma-ray flash temporarily ionized the upper layers of Earth's atmosphere, even from halfway across the galaxy. For 0.2 of a second, this single object outshone the full moon in gamma-ray light, making it the brightest transient event ever recorded from beyond our solar system. It was a stark reminder that the quietest-looking point of light in the sky could be harboring a ferocious, magnetic heart capable of shaking the galaxy itself. To fully grasp the sheer power contained within a magnetar, we need look no further than a specific historical event that took place on December 27, 2004. On that day, a magnetar officially catalogued as SGR 180620 located a staggering 50,000 light-years away in the constellation Sagittarius, decided to remind the galaxy of its presence. Within a mere 0.2 of a second, a catastrophic starquake ripped through its ultra-dense crust, causing its immense magnetic field to suddenly reconfigure. This released a giant flare of gamma rays and X-rays so concentrated and powerful that it represents the single brightest transient event ever recorded from outside our solar system. The numbers involved are almost paralyzing. That brief flash of radiation, lasting less time than the blink of an eye, carried more energy than our Sun has released over the last 100,000 years. For that fleeting moment, this single tiny object outshone the full moon in the gamma-ray sky, a feat that requires an almost incomprehensible concentration of power. But the most remarkable part of this story is that we didn't just observe it from a safe distance. We felt its effects right here on Earth. The blast of high-energy radiation traveled for 50,000 years through the void of interstellar space and finally reached our planet. When it struck the upper atmosphere, it had a measurable physical impact. The intense flash of X-rays and gamma rays caused a sudden and dramatic ionization of our planet's ionosphere, the layer of the atmosphere that reflects long-range radio waves. It was as if a cosmic flashbulb had gone off, temporarily pushing the ionosphere to a lower altitude and significantly increasing its electron density. This disruption was strong enough to be detected by instruments around the globe, and it actually caused a minor, temporary distortion in long-wave radio transmissions. To be clear, this wasn't a catastrophic event for modern technology, but it was a profound demonstration of astrophysics in action. An event that occurred from an object halfway across the Milky Way galaxy was powerful enough to physically alter our local environment, a testament to the raw, unbridled fury that magnetars are capable of unleashing. It serves as a humbling reminder of our place in a cosmos where a solitary, city-sized object can, without warning, shout its existence so loudly that the very sky of our world is forced to listen. But just when you thought stellar death couldn't get any more dramatic, the universe has reserved its most spectacular finales for the true titans of the cosmos. We are about to explore a supernova so utterly complete, so devastatingly powerful, that it erases a star from existence entirely, leaving not even a black hole or neutron star behind as a grave marker. This is the pair instability supernova, a runaway thermonuclear explosion of such pure, unadulterated force that it represents the ultimate cosmic fireworks display. To understand how this happens, we have to venture into the realm of the truly massive. We are no longer talking about stars that are simply large. We are talking about stellar behemoths in the early universe, with estimated masses between 150 and 250 times that of our Sun. In the core of such a monster, the temperatures and pressures are so extreme that nuclear fusion is happening at a ferocious rate, producing an unbelievable flood of high-energy gamma-ray photons. In normal stars, this radiation pressure pushing outward is what perfectly balances the star's immense gravity pulling inward, creating a stable structure. But in these ultra-massive stars, something truly bizarre occurs. The gamma rays in the core become so energetic that they spontaneously transform from pure energy into pairs of matter and antimatter, specifically electrons and their antimatter counterparts, positrons. This is Einstein's famous E equals mc squared in reverse, with energy congealing directly into particles. This process, known as pair production, is a cosmic catastrophe in the making. Those gamma-ray photons were providing the crucial outward pressure that was holding the star up against its own gravity. When they suddenly vanish, replaced by particle pairs, that supporting radiation pressure essentially evaporates. It is as if a building's central support pillars were instantly turned into sand. With the outward pressure gone, there is nothing left to resist the crushing force of gravity. The star's core begins to collapse inward, just as it does in a regular core collapse supernova. But here is where the story diverges in the most spectacular way possible. This implosion is so violent and heats the core to such an extreme temperature that it triggers a runaway explosion of oxygen fusion. This isn't a gentle burning, it's a thermonuclear bomb of stellar proportions. The fusion reaction releases so much energy so quickly that it doesn't just create a shock wave, it completely overwhelms the star's gravity. The entire star, from its core to its outermost layers, is blasted completely apart in a titanic explosion. There is no second collapse, no formation of a neutron star, no last-second creation of a black hole. Every single bit of the star is vaporized and hurled out into space at incredible velocities. The energy released is mind-boggling, outshining an entire galaxy for months and ejecting vast quantities of newly forged heavy elements. A pair instability supernova is the universe's ultimate act of stellar sacrifice, a total self-immolation that leaves nothing behind but a brilliant, expanding cloud of glowing gas, a ghostly echo of a star that was simply too massive to die any other way. Following the mind-bending power of a pair instability supernova, we must now turn our attention to a far more subtle, yet equally crucial, player in these cosmic explosions. While our telescopes capture the brilliant light shows, the true workhorse of a stellar detonation is a ghostly, almost undetectable particle called the neutrino. In the heart of a collapsing stellar core, for every single photon of visible light that eventually escapes to illuminate the galaxy, a staggering 100 billion neutrinos are produced and race outwards unimpeded. These particles are so tiny they are almost massless, electrically neutral, and they interact with normal matter so feebly that they can pass through light years of lead without a single collision. This aloof nature is precisely what makes them so vital to the explosion mechanism. During the core collapse of a massive star, the incredible densities trap the light and heat, bottling up the energy. But the neutrinos, born from the frantic conversions of protons and electrons into neutrons, are initially trapped as well, forming a dense neutrino sphere just outside the nascent neutron star. For a critical 10 seconds, this trapped sea of neutrinos contains an almost unimaginable amount of energy, accounting for a full 99% of the supernova's total energy budget. It is the slow diffusion of these neutrinos out of the core and their eventual escape that carries away the gravitational binding energy of the neutron star, allowing it to cool and stabilize. More importantly, as this neutrino wind finally blows free, it delivers a powerful neutrino kick to the stalled shockwave, helping to power it through the dense outer layers of the star and ultimately trigger the explosive unbinding of the entire stellar envelope. We are not just passive observers of this neutrino exodus. In one of the most profound moments in observational astronomy, on February 23, 1987, detectors on Earth recorded a pulse of 24 neutrinos. These had traveled for 160,000 years from a supernova in the Large Magellanic Cloud, supernova 1987A. For about 13 seconds, 3 separate instruments thousands of miles apart registered these ghostly messengers, arriving several hours before the first light from the explosion reached Earth. This detection was a monumental confirmation of our core collapse models. It proved definitively that the central engine of a supernova is the formation of a neutron star, and that the neutrino burst is a fundamental, predicted part of the process. Catching these elusive particles gave us a direct, real-time probe into the very heart of a star in its final, catastrophic moments, opening an entirely new window onto the most violent processes in the universe. While the universe puts on its brilliant light shows, there is another, far more stealthy form of shrapnel constantly screaming through the cosmos, a torrent of high-energy particles that we are only just beginning to understand. These are cosmic rays, and they are the silent, invisible messengers of the universe's most violent events. Unlike the light from a supernova or the gamma rays from a burst, cosmic rays are not photons. They are the atomic nuclei of elements, stripped of their electrons and accelerated to velocities so close to the speed of light that they carry unbelievable amounts of kinetic energy. The most energetic cosmic rays, dubbed "oh my God" particles, carry the kinetic energy of a professionally thrown baseball, all compressed into a single subatomic proton. These particles are the shrapnel from cosmic explosions, flung across the galaxy by the same shock waves that create the beautiful nebulas we see through our telescopes. But how does a stellar explosion act as a natural particle accelerator? The process is one of the most elegant and powerful in all of astrophysics. When a supernova's blast wave expands into the surrounding interstellar medium, it creates a colossal, moving wall of energized gas and magnetic fields. This shock front travels at thousands of kilometers per second, and as charged particles, mostly protons and the nuclei of heavier atoms, encounter this wall, they become trapped. They bounce back and forth across the shock front, held in place by the tangled magnetic fields, gaining a little more speed with each crossing. This mechanism, known as Fermi acceleration or diffusive shock acceleration, acts like a natural, universe-sized version of the Large Hadron Collider. Over days, weeks, or even centuries, these particles are pumped with energy until they are finally flung out into the galaxy, traveling on spiraling paths along the magnetic field lines that weave between the stars. Our own planet is constantly bathed in this cosmic downpour. Every second, thousands of these high-energy particles from distant cataclysms slam into the upper layers of our atmosphere. When they collide with the nuclei of air molecules, they create a spectacular secondary shower of subatomic particles, a cascade that rains down to the surface. It is a silent, invisible reminder of the violent cosmos we inhabit, a permanent link between the quiet of our atmosphere and the distant, explosive deaths of stars. The very air we breathe is continually being subtly ionized by this rain from space, a testament to the enduring power of stellar explosions to shape our local environment in ways we are only just beginning to measure. Even our own seemingly peaceful Milky Way galaxy bears the scars of a violent past, a testament to the fact that no cosmic neighborhood is truly safe from these titanic outbursts. For years, astronomers had no inkling of a colossal structure lurking in the heart of our own galaxy, hidden from our view simply because we were looking at the universe with the wrong kind of eyes. That all changed with the launch of NASA's Fermi Gamma Ray Space Telescope in 2008. Its mission was to survey the high-energy sky, and what it revealed was both unexpected and magnificent. Two enormous, symmetrical bubbles of gamma-ray emission, one ballooning out from the galactic center north of the plane of the Milky Way, and the other extending an equal distance to the south. These are the Fermi bubbles, and their scale is almost beyond human comprehension. Each bubble stretches for a staggering 25,000 light-years from end to end. To put that in perspective, the entire diameter of our galaxy is about 100,000 light-years, meaning these structures encompass nearly half the height of the Milky Way. If our eyes could see in gamma-ray light, these bubbles would dominate the night sky, appearing as large as the Big Dipper or Orion. For them to have remained undiscovered for so long speaks to the quiet, invisible nature of this high-energy radiation, a form of light that is completely blocked by our atmosphere and requires sensitive instruments in space to detect. The bubbles are not static, they are a dynamic, ongoing phenomenon with edges that are remarkably sharp and well-defined, suggesting they are the result of a single, relatively recent and incredibly powerful event. Within these vast structures, gas is seething with energy, emitting gamma rays as it interacts with the galaxy's magnetic field and a sea of high-speed electrons. The sheer size and energy of the Fermi bubbles point to one inescapable conclusion. Our galaxy's supermassive black hole, Sagittarius A, which today is a relatively quiet and docile giant, must have experienced a period of intense activity in the not-too-distant cosmic past. This was not a mere burp, it was a full-throated roar that echoed through the entire galactic system. The leading theory suggests that several million years ago, Sagittarius A underwent a major accretion event. A substantial cloud of gas, or perhaps even a star cluster, ventured too close and was torn apart, feeding the black hole a colossal meal. This sudden influx of material ignited the central engine, powering it into a brief but spectacular state of activity. The result was the launch of two opposing relativistic jets, or a single, massive outflow of energy directly from the black hole's poles, blasting their way out of the galactic disk and inflating these immense gamma-ray emitting lobes that we see today. This event would have been a cataclysm for any fledgling planetary systems in its path, but from our safe distance of 26,000 light-years, it provides us with a front-row seat to study the aftermath of a quasar-like eruption right in our own cosmic backyard, a permanent monument to the fact that even our own galaxy is not immune to the universe's most energetic explosions. While we often think of these colossal stellar explosions as events from the distant cosmos or the ancient past, one of the most dramatic preludes to a future supernova is unfolding right now in our own galactic neighborhood, a mere 7,500 light-years away. In the southern constellation of Carina lies the Eta Carinae system, a true ticking time bomb of a star. During the 1840s, this star did something that astonished astronomers of the day and continues to puzzle us now. It underwent what we now call the Great Eruption, a stellar tantrum of unprecedented scale. Over the course of several years, Eta Carinae brightened spectacularly, and by 1843, it had become the second brightest star in the entire night sky, outshone only by Sirius despite its vast distance. This was not a clean, sudden explosion like a supernova, but a prolonged, violent paroxysm where the star ejected an enormous amount of its own mass, the equivalent of at least 10 times the mass of our entire Sun, at speeds approaching millions of kilometers per hour. This material didn't just drift away, it formed two vast, expanding lobes of gas and dust that we see today as the spectacular Homunculus Nebula, a name that means little man due to its shape as seen through early telescopes. This nebula is the ghost of that 19th century eruption, a cosmic fossil record of a star's struggle against its own immense gravity. What caused this bizarre, non-terminal eruption? Eta Carinae is not a single star but a binary system with a primary star that is a true hypergiant, containing the mass of roughly 150 suns, placing it right on the precipice of the theoretical upper limit for stellar existence. The leading theory suggests that in the 1840s, the primary star became so luminous that the outward pressure of its own radiation began to overwhelm the inward pull of its gravity. This radiation-driven instability caused the star's outer layers to balloon outward, becoming so extended and loosely bound that even the gravitational tug of its companion star could help strip them away in a series of massive outbursts. It was a stellar hurricane powered by the star's own light. The Great Eruption was very likely a supernova imposter event, a catastrophic release of energy that mimics the power of a true supernova but falls just short of completely destroying the star. Eta Carinae survived, but it was forever changed, shrouded in the very veil of dust it created. Today, the star remains highly unstable, a variable and unpredictable beacon wrapped in the beautiful, eerie glow of its own expelled guts. The Homunculus Nebula continues to expand, and at its heart, the titanic binary stars whip around each other in a chaotic 5.5-year orbit, their fierce stellar winds colliding and creating intense shocks that glow in X-rays. For astronomers, Eta Carinae is a living laboratory, a rare chance to study the final, volatile stages of a star's life just before it goes supernova. And go supernova it will, and likely sooner rather than later in cosmic terms, perhaps within the next 100,000 years, maybe even tomorrow. When it finally does explode, it will be a spectacle unparalleled in human history. Located safely outside the dangerous range, we on Earth will witness a star becoming, for a time, as bright as the full moon, visible even in broad daylight. It will be the death of a stellar titan and the birth of a new and most likely a brilliant new nebula, seeded with the heavy elements forged in its final, glorious detonation. The stability of a star's remains is one of the most delicate balancing acts in the cosmos, and nowhere is this more perfectly illustrated than in the fate of a white dwarf. After a sun-like star exhausts its nuclear fuel, it gently puffs away its outer layers, leaving behind its incredibly dense, Earth-sized core, a white dwarf. This stellar ember is no longer powered by fusion. Instead, it is supported against its own immense gravity by a bizarre quantum mechanical effect known as electron degeneracy pressure. You can think of it as a fundamental rule of the universe that forbids electrons from being squeezed into the same quantum state, creating a powerful, outward pushing force. For billions of years, this quantum pressure can successfully oppose the inward crush of gravity, allowing the white dwarf to cool slowly into a dark cosmic diamond. But this stability comes with a strict and non-negotiable upper limit. In the 1930s, the brilliant astrophysicist Subrahmanyan Chandrasekhar calculated that this electron degeneracy pressure has a breaking point. He determined that if the mass of a white dwarf exceeds approximately 1.4 times the mass of our Sun, a value now known as the Chandrasekhar limit, the force of gravity becomes overwhelmingly powerful. At this critical threshold, even the stubborn resistance of degenerate electrons fails. The white dwarf can no longer support its own weight, and it is forced to collapse. This inevitable collapse, however, does not lead to a quiet end. For many solitary white dwarfs, crossing this mass boundary would simply mean collapsing into a neutron star. But most white dwarfs exist in binary systems, and this is where the story becomes explosive. If a white dwarf has a companion star, a red giant, or even a main sequence star like our Sun, it can begin to gravitationally steal material, slowly siphoning hydrogen and helium from its partner. This stolen gas accumulates on the white dwarf's surface, increasing its mass ever so gradually over millions of years. As the white dwarf's mass creeps closer and closer to that 1.4 solar mass limit, the pressure and temperature in its core skyrocket. When it finally reaches the Chandrasekhar limit, the conditions become so extreme that a runaway nuclear fusion reaction is triggered, not in the gathered hydrogen on the surface, but deep within the star's heart, where carbon fusion ignites almost instantaneously throughout the entire degenerate core. This is not a gentle burn, it is a total thermonuclear detonation. The entire white dwarf is torn apart in a cataclysm so violent and so uniform that it constitutes a Type Ia supernova. In a matter of seconds, the star is completely unbounded, releasing an amount of energy equal to the total output of a typical galaxy. What makes this specific explosion so invaluable to astronomers is its remarkable consistency. Because every Type Ia supernova is triggered by a white dwarf reaching the exact same critical mass, they all explode with almost identical intrinsic brightness. This makes them the gold standard of cosmic distance markers, known as standard candles. When astronomers observe a Type Ia supernova in a distant galaxy, they can measure how bright it appears from Earth and, knowing its true brightness, calculate its distance with extraordinary precision. It was by using these stellar mileposts that two independent teams of astronomers made the Nobel Prize-winning discovery in the late 1990s that the expansion of the universe is not slowing down, as everyone had expected, but is actually accelerating, driven by a mysterious force we now call dark energy. So this single, precise mass limit, a number calculated on paper nearly a century ago, does more than just dictate the death of a star. It provides the fundamental ruler we use to measure the scale, history, and ultimate fate of the entire cosmos. This precise and predictable nature of Type Ia supernova made them the perfect tool for one of the most ambitious projects in the history of cosmology, measuring the ultimate fate of the universe itself. For most of the 20th century, the prevailing scientific view was that the cosmos, while expanding from the Big Bang, must be slowing down. The mutual gravitational pull of all the matter in the universe, the galaxies, the gas, the dark matter, was thought to be acting like a cosmic brake, gradually decelerating the expansion. The central question for astronomers was whether this deceleration was sufficient to one day halt the expansion and pull everything back together in a big crunch, or whether the universe would simply coast onward, expanding forever at an ever-slowing rate. To answer this, they needed to measure the expansion rate at different epochs in cosmic history, effectively looking back in time to see how the universe's growth has changed. This is where the Type Ia supernova became indispensable. Think of them as identical light bulbs scattered across the cosmos. If you know the true wattage of the bulb, you can calculate its distance by how dim it appears. A supernova in a relatively nearby galaxy gives you a calibration point. Its redshift tells you how fast its galaxy is receding due to the universe's expansion, and its apparent brightness tells you its precise distance. By comparing these two measurements for many local supernovae, astronomers could pin down the current expansion rate, a value known as the Hubble constant. But the real magic happens when you look far, far away. Because light takes time to travel, observing a supernova in a galaxy billions of light years away is like looking billions of years into the past. By finding these ancient standard candles and measuring their brightness and redshift, astronomers could determine not just how fast the universe was expanding then, but also how that expansion rate has changed over cosmic time. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to do exactly this. They painstakingly searched for these distant stellar explosions, expecting to confirm the gradual deceleration of the cosmos. What they found, however, sent a shockwave through the foundations of physics. The data from the most distant supernova were consistently fainter than they should have been. This meant they were farther away than their redshifts indicated. The only possible explanation was that the expansion of the universe was not slowing down at all. In fact, it was speeding up. Something was overpowering the collective gravity of all the matter in the cosmos, pushing galaxies apart from one another at an ever-increasing rate. This monumental discovery that the universe is undergoing accelerated expansion was so revolutionary and so counter to all expectations that the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011. The entity responsible for this cosmic acceleration was dubbed dark energy, a name that perfectly captures our profound ignorance of its true nature. We cannot see it, we cannot directly detect it, but we can observe its overwhelming effect on the largest scales of reality. It appears to be a property of empty space itself, a repulsive force that comprises roughly 68% of the total energy content of the universe, dominating the cosmic budget and dictating the ultimate fate of everything. Without the precise, standardized flash of Type Ia supernova acting as our cosmic lighthouses, we might never have stumbled upon this deepest and most mysterious secret of the cosmos. Moving from the certainties of measured cosmic explosions to a single, enduring mystery brings us to one of the most tantalizing and debated anomalies in the history of astronomy. On the evening of August 15, 1977, a radio telescope known as the Big Ear, operated by Ohio State University, was performing a routine survey of the sky. It was programmed to scan for narrowband radio signals, a type of emission that is rarely produced by natural cosmic phenomena, but is a hallmark of human technology, like our own radio and television broadcast. As the Earth rotated, the telescope's focus drifted through the constellation Sagittarius, and for exactly 72 seconds, it recorded something extraordinary. A few days later, a volunteer named Jerry Amon was reviewing the computer printout, its columns filled with alphanumeric codes representing signal intensity. His eye caught a sequence of characters so startling that he circled them in red pen and wrote a single, now iconic word in the margin: wow. The signal, designated 6EQUJ5, was a burst of radio waves at a frequency of 1,420 MHz, a frequency that is protected spectrum, meaning terrestrial transmitters are forbidden from using it so that radio astronomers can listen to the universe in silence. It was billions of times stronger than the background radio noise of space. It appeared, peaked, and then vanished, following a perfect curve that matched what you would expect from a stationary, distant source being scanned by the telescope's rotating beam. And then it was gone. Despite numerous attempts over the decades to find it again, the wow signal was never repeated. Its one-time nature is what makes it so compelling and so frustrating. If it were a human satellite or a reflected signal from the Earth's surface, it would have been predictable and repeatable. If it were a known astrophysical event, like a supernova or a gamma-ray burst, it would have left other signatures across the electromagnetic spectrum. The wow signal remains a ghost, a single, perfect data point in a sea of cosmic static. The most exciting, though statistically remote, possibility is that it was an artificial transmission from an extraterrestrial intelligence. The combination of its strength, its narrowband nature, and its location in a quiet part of the radio spectrum fits the profile of a deliberate beacon perfectly. However, the scientific community largely favors a natural, if still unknown, astrophysical explanation. The leading theories suggest it could have been an incredibly powerful and rare type of radio transient, perhaps the emission from a comet that wasn't known at the time, or a novel kind of stellar flare or interaction that we have yet to properly categorize. It serves as a powerful reminder that for all we have learned about the violent, energetic universe, there are still phenomena that defy our current understanding. Brief flashes in the cosmic dark that challenge us to keep listening, keep watching, and remain open to the possibility of the truly unexpected. Just when we thought we had a handle on the universe's energetic repertoire, a new and deeply mysterious class of signal began to appear, one so fleeting and powerful that it has become one of the most active and puzzling frontiers in modern astrophysics. These are fast radio bursts, or FRB. Imagine a flash of radio light, a burst of energy at the frequencies used for FM radio and television broadcasts. Now compress all the energy our sun emits over nearly a full century into that single flash, and squeeze its entire duration into a few thousandths of a single second. That is the essence of an FRB, a cosmic blink so brief you would miss it if you weren't looking at exactly the right place at exactly the right time. The first known FRB was discovered not in real time, but by sifting through archived data in 2007, a burst from 2001 that had been recorded but overlooked. This single event, now known as the Lorimer burst, hinted at an entirely new phenomenon. For years, it stood alone, a potential oddity that some dismissed as a terrestrial glitch. But then more were found, confirming that these were indeed real, highly energetic, and coming from far beyond our galaxy. The sheer distance to these events is a key part of their mystery. As these radio waves travel across millions or even billions of light-years of intergalactic space, they pass through a diffuse sea of free electrons. This material has a subtle but measurable effect, scattering the different radio frequencies and causing the higher frequencies to arrive at our telescopes a tiny fraction of a second before the lower ones. This effect, called dispersion, allows astronomers to calculate the total amount of material the signal has passed through and thus estimate its colossal distance. We now know that FRBs are extragalactic, originating from sources far outside the Milky Way, which makes their incredible brightness all the more astonishing. The race to understand what could possibly generate such a short, sharp, and fantastically energetic signal has led to a zoo of theoretical models, ranging from the plausible to the highly speculative. The leading candidate involves objects we've already met, magnetars. We know these ultramagnetic neutron stars are capable of producing enormous bursts of energy, like the giant flares that can ionize our atmosphere from across the galaxy. It is thought that a starquake on a magnetar in a distant galaxy could release a magnetic shockwave powerful enough to generate a brilliant, one-off FRB. This theory gained tremendous support in April 2020, when a magnetar within our own Milky Way galaxy erupted with a radio burst that, while not as powerful as the extragalactic FRBs, shared many of the same characteristics. It was a smoking gun, strongly suggesting that at least some FRBs are indeed the voices of these magnetic monsters, but the plot thickens considerably. While many FRBs are one-off events, a growing number of sources have been observed to repeat, firing off multiple bursts from the same location in the sky with no predictable pattern. This repetition is a game-changer, as it rules out any model involving the total destruction of the source, like a stellar collision or a black hole merger. For repeating FRBs, astronomers need a mechanism that can fire again and again, perhaps driven by the complex and evolving magnetic field of a young, hyperactive magnetar, or the violent interactions within a dense binary system. The most famous repeater, known as FRB 121102, has been caught in outburst numerous times, providing a wealth of data that has allowed scientists to pinpoint its home galaxy, a small, unassuming dwarf galaxy over 3 billion light-years away. The ability to localize these bursts to specific galaxies has opened up a new and unexpected application for them as probes of the cosmic web. The diffuse, invisible material that lies between galaxies is notoriously difficult to study. But when an FRB signal travels through this material, its dispersion measure gives us a direct reading of the total number of electrons along the line of sight, allowing us to literally weigh the missing matter in the universe. So, even as we strive to understand what these objects are, we are already using them as powerful tools to map the large-scale structure of the cosmos. The enigma of fast radio bursts perfectly captures the dynamic nature of astronomy. They represent a phenomenon that was entirely unknown just over a decade ago, a sudden and brilliant puzzle appearing in a seemingly quiet part of the spectrum. Their existence reminds us that for all we have learned about supernova and gamma-ray bursts, the universe still holds surprises whispering, or perhaps shouting, its secrets in forms we are only just beginning to perceive. The discovery of repeating fast radio bursts fundamentally rewrote the script on what we thought was possible. For years, the leading hypothesis was that these incredibly brief, energetic flashes were the final death cries of cosmic objects, a single, catastrophic event that destroyed the source, perhaps a neutron star collapsing into a black hole or two ultra-dense objects merging. The idea was that such an immense release of energy must necessarily be a one-time only event. That entire line of thinking was turned on its head in 2016 when the Arecibo radio telescope in Puerto Rico observed something unprecedented. A source known as FRB 121102, which had first been detected in 2012, did something extraordinary. It burst again, and then it did so again and again, firing off multiple powerful radio flashes with no regular pattern. This was not a cosmic cataclysm, this was a repeater. The confirmation of repeating FRBs was a watershed moment. It immediately and decisively ruled out any model that involved the total annihilation of the source. You cannot have a star explode multiple times. The event is, by its very nature, final. This meant the engine powering these bursts had to be something that could survive its own outburst, an object with a mechanism that could fire again and again, storing and releasing phenomenal energy without tearing itself completely apart. The scientific community scrambled to explain how a single source could generate such prodigious power repeatedly. The prime suspect quickly became the most magnetic and volatile objects we know of, magnetars. The theory suggests that a young, hyperactive magnetar, still settling after its violent birth in a supernova, could be surrounded by a complex and turbulent environment. Intense starquakes on its solid crust or sudden reconnections of its unimaginably powerful magnetic field lines could release magnetic shocks. These shocks would then travel through a thick, magnetized nebula of material left over from the supernova, and as they interact with this plasma, they could generate the brilliant milliseconds-long radio flashes we detect as FRBs. This model beautifully explains the repetition. The magnetar remains intact, its internal stresses building and releasing over time. It also accounts for the incredible energy, as we know magnetars are capable of such violent outbursts. The repeating nature of these signals also gave astronomers an invaluable gift, a second chance. With a one-off burst, you get one fleeting moment of data, and then the source vanishes forever, leaving countless questions unanswered. But with a repeater, you can point the world's most powerful telescopes at its known location and wait. You can observe it across the entire electromagnetic spectrum in radio, optical, and X-ray light to see if there is any other activity associated with the burst. This is exactly what happened with FRB 121102. By tracing its precise location, astronomers found it resided in a small, faint, and unassuming dwarf galaxy over 3 billion light-years away, a galaxy that was actively forming new stars. This environmental clue was another piece of the puzzle, strongly suggesting that repeating FRBs are linked to young stellar populations, the very places where newborn magnetars would be found. The repeating signals transformed FRBs from mere curiosities into persistent, addressable cosmic laboratories, allowing us to slowly but surely unravel the physics of the most enigmatic beacons in the universe. While we often look billions of light-years away to witness cosmic violence, one of the most dynamically explosive objects in the universe is in fact our very own Sun. It may seem like a placid, constant ball of light from our earthly perspective, but it is a seething, magnetically active star, capable of eruptions that, while minuscule compared to a supernova, pack a punch that can directly reach out and touch our modern technological civilization. These solar tantrums come in two primary, related forms: the intense flash of a solar flare and the colossal, slower-moving cloud of a coronal mass ejection. A solar flare is a sudden, rapid, and intense explosion on the Sun's surface that occurs when the energy stored in its twisted magnetic fields, often above sunspot groups, is suddenly released. This process, known as magnetic reconnection, is like cutting a tensely wound rubber band. The magnetic field lines snap and reconfigure into a more stable arrangement, converting immense magnetic energy into kinetic and thermal energy in a matter of minutes. The result is a localized blast that heats solar material to tens of millions of degrees, causing it to emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The energy released in a major solar flare can be equivalent to millions of 100 megaton hydrogen bombs exploding simultaneously, all concentrated into a relatively small area of the solar surface. This flash of high-energy radiation travels at the speed of light, reaching Earth in just over 8 minutes. While our atmosphere shields us from the direct physiological effects, this radiation surge can have immediate consequences. It ionizes the upper layer of our atmosphere, the ionosphere, which can degrade or even black out high-frequency radio communications used by aviation, shipping, and emergency services. It can also pose a radiation hazard to astronauts in orbit and can interfere with the electronics and sensitive instrumentation on satellites, but the flare is often just the opening salvo. The same magnetic reconnection event that causes a powerful flare can also unleash something far larger and more impactful, a coronal mass ejection or CME. Think of a solar flare as the brilliant muzzle flash and the CME as the cannonball. A CME is a massive billion-ton cloud of solar plasma, a soup of protons, electrons, and magnetic fields that is violently hurled away from the Sun into interplanetary space. These colossal structures can expand to become larger than the Sun itself as they travel outward, and they move at staggering speeds, ranging from a relatively slow 250 kilometers per second to an astonishing 3,000 kilometers per second for the most extreme events. While the light from a flare reaches us in minutes, a CME takes time to traverse the 150 million kilometers to Earth, typically arriving anywhere from half a day to 3 days after the initial eruption. When a CME is aimed directly at Earth, the consequences of its arrival can be profound. Our planet's magnetic field acts as a protective shield, deflecting most of the continuous stream of particles from the solar wind. But a powerful CME is a different beast altogether. It is a massive magnetized shockwave that compresses and distorts our planet's magnetic field in an event known as a geomagnetic storm. This rapid distortion induces powerful electrical currents in the ground and in long human-made conductors like power lines, pipelines, and undersea communication cables. The most famous example of this occurred in September 1859 during what is now known as the Carrington event, a colossal solar storm so powerful that auroras were seen as far south as the Caribbean, caused telegraph systems, the advanced technology of the day, to fail spectacularly. Telegraph operators received shocks, papers caught fire from the electrical surges, and some lines continued to operate even after being disconnected from their power sources, powered entirely by the celestial currents induced in the wires. A storm of that magnitude today would have catastrophic consequences for our far more electrically dependent world. It could cause widespread and prolonged power grid blackouts affecting millions, permanently damage critical high-voltage transformers that take years to replace, and cripple global satellite networks that we rely on for GPS, communications, and weather forecasting. The economic impact of such an event is estimated to be in the trillions of dollars, with a recovery period that could last for years. This is not merely speculative fiction. In March 1989, a much smaller solar storm than the Carrington event caused the complete collapse of Quebec's power grid, leaving 6 million people without electricity for 9 hours and providing a stark, modern-day warning of our vulnerability to the sun's fury. This brings the reality of cosmic explosions from the abstract, distant universe right to our doorstep, demonstrating that even our local star, the source of all life, remains a powerful and occasionally temperamental force that demands our respect and understanding. To grasp the full force of our sun's temper, we need only look back to the first days of September 1859, a period when modern technology got its first taste of cosmic weather. The event began with an English astronomer named Richard Carrington. On the morning of September 1st, while sketching a large group of sunspots through his private telescope, Carrington witnessed something unprecedented. Two patches of intensely bright white light erupted from the sunspots, overwhelming his instrument's protective filters. He was stunned, realizing he was observing a massive solar flare in real time. What made this event so extraordinary was what followed less than 18 hours later. A coronal mass ejection of almost unimaginable scale, directly aimed at Earth, slammed into our planet's magnetic field. The resulting geomagnetic storm was so powerful that it pushed the auroral oval, normally confined to polar latitudes, down across the entire globe. The night skies erupted in a firestorm of color. In the Caribbean, people in Cuba and Jamaica watched in awe and terror as crimson and green curtains of light filled the heavens. So brilliant was the display over the Rocky Mountains that gold miners in the high camps woke up and began making breakfast, convinced the dawn had arrived. The light was so intense that newspapers in northeastern cities could reportedly be read outdoors at midnight by the eerie, shimmering glow. But the true measure of the storm's power was written not in the sky, but in the wires of the world's most advanced communication network, the telegraph system. As the Earth's magnetic field convulsed under the solar assault, it induced massive electrical currents in the telegraph lines. Operators received severe shocks from their equipment, and telegraph papers spontaneously caught fire. Even more bizarrely, some lines continued to operate and transmit messages even after being disconnected from their power sources, running solely on the celestial currents flowing through the atmosphere. The entire technological nervous system of the mid-19th century was thrown into chaos by a blast of plasma from 93 million miles away. Modern analysis suggests the Carrington event was a perfect storm of solar fury. It likely involved not one, but two consecutive coronal mass ejections, with the first one clearing a path through the solar wind, allowing the second, more powerful blast to travel to Earth with unprecedented speed and efficiency. If an event of identical magnitude were to strike today, the consequences would be exponentially more severe. Our deeply interconnected, electrically dependent civilization is far more vulnerable than the world of 1859. The immense currents induced by such a storm could overwhelm high-voltage power transformers, which are the backbone of continental power grids. These transformers are not stockpiled. They are custom-built, and replacing a large number of them could take years, leading to prolonged, widespread blackouts affecting hundreds of millions of people. Satellite operations would be crippled, disrupting global positioning, communications, and weather forecasting. Financial networks, water distribution systems, and fuel supply chains would grind to a halt. Studies estimate the total economic impact could reach into the trillions of dollars, with a recovery period that could last for a decade. The Carrington event stands as a stark and sobering historical benchmark, a permanent reminder that our local star, the source of all life and warmth, is also capable of unleashing a fury that can reach across the void and fundamentally challenge our technological existence. It connects the most energetic explosions in the distant cosmos directly to our daily lives, proving that space weather is not an abstract concept, but a genuine and potent force that we must learn to predict, prepare for, and respect. Considering the spectacularly violent endpoints of massive stars, our own Sun provides a remarkably gentle and almost poetic contrast in its final act. It is a destiny not of self-annihilation, but of quiet transformation, a cosmic retirement that highlights how a star's death is dictated entirely by the weight it has carried throughout its life. Our Sun is a star of modest proportions, a main sequence star that has been burning hydrogen into helium in its core for nearly 5 billion years. It has enough fuel to continue this stable existence for another 5 billion, a testament to its incredible efficiency and stability. But this stability is also what guarantees a far less explosive finale than the hypernova and supernova we have explored. The key difference lies in mass. A star must be at least 8 times more massive than our Sun to even have a chance at a core collapse supernova. Our Sun simply does not have the gravitational muscle to push its core to the extreme temperatures and pressures needed to fuse elements all the way up to iron. Instead, its journey toward retirement will begin in about 5 billion years when it finally exhausts the hydrogen fuel in its core. With the central fusion furnace sputtering out, the balance that has held the Sun stable for 10 billion years will be broken. Gravity, no longer opposed by the outward push of radiation from fusion, will begin to crush the core. This compression, however, will heat the core until it reaches a new threshold, triggering the fusion of the helium that has been accumulating there for billions of years. This is the beginning of the Sun's red giant phase. The ignition of helium fusion is a more volatile process, and the sudden release of energy will cause the Sun to swell dramatically. Its outer layers will expand outward at a tremendous rate, cooling as they go, turning the Sun from a yellow main sequence star into a vast, bloated red giant. This expansion will be absolute and merciless. The Sun's outer atmosphere will swell to engulf the orbits of Mercury and Venus, and while it may stop just short of completely swallowing Earth, our planet will be scorched to a cinder, its oceans boiled away and its crust melted into a global sea of lava. The sun will dominate the sky, a dull red orb of immense searing heat. For a billion years or so, the sun will exist in this unstable state, fusing helium into carbon and oxygen in its core. This is the critical pivot point in its life cycle. When the helium in the core is finally exhausted, the sun will once again face a fuel crisis. It will attempt to contract its core to ignite carbon fusion, but here its modest mass becomes its defining characteristic. A star like the sun simply does not have enough gravitational pressure to raise its core temperature to the 600 million degrees required to fuse carbon. The fusion process stops at carbon and oxygen. The star's core, now composed of these elemental ashes, will contract one final time, but it will not collapse. Instead, it will be supported by a bizarre quantum mechanical force known as electron degeneracy pressure. This is not a force driven by heat or motion, but by a fundamental law of physics, the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. As gravity tries to squeeze the core's electrons together, this principle creates an irresistible outward pressure that finally halts the crush of gravity. The core has become a white dwarf, an Earth-sized sphere containing nearly the entire mass of the original star, a diamond-like ember so dense that a single teaspoon of its material would weigh many tons on Earth. This nascent white dwarf will be intensely hot, glowing with a fierce white heat from the residual thermal energy of its formation. But this is only half of the story, and it's the other half that creates one of the most beautiful sights in the cosmos. While the core is settling into its new life as a white dwarf, the star's outer layers are experiencing a different fate. During its red giant phases, the sun becomes so large that its gravitational grip on its outermost layers becomes incredibly weak. Through a series of powerful pulsations and a relentless, steady stellar wind, the sun will gently blow these outer layers into space over a period of tens of thousands of years. This ejected shell of gas, now completely detached from the star, will form a vast, expanding cloud around the exposed white dwarf, and here the final act of stellar alchemy occurs. The invisible but intense ultraviolet radiation pouring from the searing hot surface of the white dwarf floods into this expanding cloud of gas. This high-energy light ionizes the gas, stripping electrons from their atoms and causing the entire nebula to fluoresce with a spectacular, ethereal glow. This is the birth of a planetary nebula, a name that is a complete misnomer from the 18th century, when astronomers through their small telescopes thought these faint, round objects looked like the disks of distant planets. In reality, they are the glowing shrouds of dead stars, the intricate structures of planetary nebulae. Their delicate shells, bipolar lobes, and complex knots are sculpted by the interactions of the slow, dense wind from the red giant phase and a later, fast wind from the hot white dwarf. They are short-lived cosmic artworks, visible for only perhaps 10,000 to 20,000 years before the gas expands and disperses too thin to glow, mixing its enriched material back into the interstellar medium. The white dwarf at the center, no longer powered by fusion, will then simply cool down over billions of years, slowly fading from white to yellow to red, and eventually to a cold black dwarf, a dark crystalline sphere of carbon and oxygen, a permanent monument to a star that was. So, while the death of a massive star is a brief, violent explosion that forges heavy elements and scatters them far and wide, the death of a star like our Sun is a prolonged, beautiful process of shedding its outer layers to reveal its dense, degenerate core. It is a cosmic cycle of rebirth, where the death of one star provides the enriched gas and dust that will one day coalesce into new stars, new planets, and perhaps even new life. Our Sun will not go out with a bang, but with a whisper, leaving behind a jewel-like core encased in a temporary, luminous veil of its own making. But for all the brilliant violence we see scattered across the cosmos, the visible universe, the stars, the galaxies, the supernovae, is only a tiny fraction of the actual story. In reality, the light and energy we observe are just the glittering surface froth on a deep, dark ocean of forces we cannot see. The cosmic stage upon which these explosions perform is built and shaped by two invisible architects, dark matter and dark energy. They don't cause the explosions themselves, but they dictate the entire environment, the cosmic geography, that makes these events possible in the first place and will ultimately determine their final, distant future. Think of it like this: if a gamma-ray burst is the spectacular eruption of a volcano, then dark matter is the entire tectonic plate that built the mountain range, and dark energy is the force that will one day rip the very continent apart. Their influence is subtle, operating on the grandest scales of space and time, but it is utterly fundamental. Let's start with dark matter. We've known of its existence indirectly since the 1930s, when astronomers like Fritz Zwicky noticed that galaxies in clusters were moving far too quickly to be held together by the gravitational pull of their visible stars alone. There simply wasn't enough visible matter to provide the necessary gravity. The same phenomenon is observed in individual galaxies, where stars at the outer edges orbit at speeds that should fling them off into intergalactic space. The only explanation is that every galaxy, including our Milky Way, is embedded within a vast, massive, and invisible halo of something that does not emit, absorb, or reflect light. This is dark matter. We call it matter because it interacts gravitationally, providing the extra pull that holds the universe's structure together. Without these massive dark matter halos, galaxies would never have formed in the first place. In the early universe, slight density fluctuations in the dark matter provided gravitational seeds. Ordinary matter, the hydrogen and helium gas that would become stars, was drawn into these dark matter potential wells. It was here, within these concentrated pools of dark matter, that the first gas clouds could collapse, fragment, and ignite into the first generation of stars. These pioneering stars were the ones that lived fast, died young, and exploded as the first supernova, seeding the cosmos with heavier elements. Every single galaxy and every single stellar explosion within it owes its existence to the gravitational scaffolding provided by dark matter. It is the invisible skeleton of the cosmic web, the framework upon which all the visible, luminous, and explosive drama of the universe is hung. While dark matter works to pull the universe together, its cosmic counterpart, dark energy, is doing the exact opposite. As we discovered through the dimming of distant Type Ia supernova, dark energy is the mysterious force driving the accelerated expansion of the universe. It behaves like a kind of anti-gravity, a repulsive force inherent to the fabric of space itself. Its nature is one of the greatest mysteries in all of physics, but its effects are unmistakable. In the present era, dark energy has become the dominant component of the cosmos, making up about 68% of its total energy density. This has profound consequences for the long-term future of everything, including the grand cycle of stellar birth and death. For billions of years, the gravitational pull of dark matter and ordinary matter was winning the cosmic tug-of-war, slowing the expansion from the Big Bang. But around 5 billion years ago, dark energy took over. Now, as the universe continues to expand at an ever-increasing rate, the large-scale structure is being steadily pulled apart. Galaxies are being isolated from one another, their gravitational ties severed. This has a direct, if slow motion, impact on the future of cosmic explosions. In the far, far future, as galaxies become more and more isolated, the reservoir of intergalactic gas from which new stars form will be cut off. Star formation will gradually cease. Without new stars being born, the primary fuel for supernova and gamma-ray bursts will eventually be exhausted. The universe will become a darker, quieter place, populated by aging stars slowly burning out. The era of frequent, brilliant stellar cataclysms will come to an end. This leads us to the most speculative and profound implications of all. Depending on the precise and still unknown properties of dark energy, several ultimate fates for the cosmos are possible. In one scenario, the acceleration continues indefinitely, leading to what is poetically called the heat death or big freeze. In this future, the universe expands forever, becoming increasingly cold and empty, with all energy eventually dissipating into a uniform, lifeless void. In a more dramatic, though less favored, model called the Big Rip, the acceleration caused by dark energy could actually intensify over time. If this were to happen, the repulsive force would eventually overcome not just the gravity between galaxies, but all forces holding structures together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems would be ripped from their stars. In the final, terrifying moments, stars and planets themselves would be shredded, and finally, atoms and even subatomic particles would be pulled apart by the escalating expansion of space itself. In this ultimate cosmic explosion, the very fabric of reality would be vaporized. While this is a speculative and extreme possibility, it underscores the incredible power that dark energy wields over the ultimate destiny of all things. Dark matter and dark energy, therefore, represent the ultimate context for every explosion we have discussed. They are the unseen directors of the cosmic play, setting the stage, guiding the action, and ultimately writing the final curtain call. The brilliant, fleeting flashes of supernova and gamma-ray bursts are the visible actors, but their story is only possible within the vast, dark theater built and ultimately destroyed by these mysterious, dominant forces of the cosmos. While our understanding of cosmic explosions has been built over decades by observatories on the ground and in space, we are now entering a new golden age of discovery, one powered by an eye in the sky so revolutionary it can see back to the dawn of time. The James Webb Space Telescope, or JWST, is not merely an upgrade to its predecessor, Hubble. It is a paradigm shift, a technological marvel designed to answer fundamental questions about the very first stars and the explosions that ended their lives. Its mission is to push our vision to the edge of the observable universe, to a period known as the Cosmic Dawn, when the first starlight began to pierce the primordial darkness. The key to this incredible power lies in its ability to see not invisible light, which our eyes perceive, but primarily in the infrared portion of the spectrum. This is not just a technical preference, it is a necessity for peering into the deepest reaches of space. Because the universe is expanding, the light from the most distant objects is stretched as it travels across billions of light years. This phenomenon, called redshift, shifts the light from its original, often ultraviolet or visible, wavelengths into the infrared. For the earliest galaxies and the supernova within them, their light is so profoundly redshifted that it becomes invisible to telescopes like Hubble. JWST, with its gold-coated beryllium mirrors and suite of super-sensitive infrared instruments, is built to catch this stretched light, essentially turning back the cosmic clock and giving us a direct view of the universe in its infancy. This new window allows us to hunt for the most elusive and consequential explosions of all, the very first supernova. Theoretical models suggest that the universe's first stars, known as population Roman III stars, were unlike anything we see today. They were likely monstrous behemoths, hundreds of times more massive than our Sun, composed of only the pristine hydrogen and helium forged in the Big Bang. Because they lacked heavier elements which act as a coolant during star formation, they could grow to incredible sizes. These titans would have lived fast and died young, their brief, brilliant lives culminating in cataclysmic pair instability, supernova, or direct collapse into black holes. The explosions of these first stars were the universe's primary act of cosmic alchemy, the first event to ever seed the void with elements heavier than helium, the carbon, oxygen, and iron that are the building blocks of planets and life itself. Before JWST, these first supernovae were purely theoretical. We had no direct observational evidence of their existence or their properties. Now, astronomers are using JWST to scan the deepest fields of the sky, searching for the unique infrared signatures of these primordial explosions. They are looking for transient points of light that appear and then fade in galaxies so distant that their light has been traveling for over 13 billion years. By analyzing the light from these ancient supernovae, scientists can determine their composition, their energy, and the mass of the star that created them, finally testing our models for how the first elements were forged and scattered across the cosmos. Beyond these first-generation supernovae, JWST is also providing an unprecedented look at more familiar, yet equally distant cataclysms. It has already observed gamma-ray burst afterglows at record-breaking distances, allowing us to study the properties of these immense explosions when the universe was only a small fraction of its current age. By dissecting the infrared light from these afterglows, JWST can determine the chemical composition of the galaxies that hosted them, revealing how quickly these early stellar systems were enriched with heavy elements. This data is crucial for understanding the timeline of cosmic chemical evolution, telling us how quickly the raw materials for planet formation and potential life became available after the Big Bang. Furthermore, JWST powerful spectrographs can peer into the hearts of stellar nurseries in nearby galaxies, observing dust-enshrouded regions that are completely opaque to visible light. Here, it can witness the final, unstable stages of massive stars like Eta Carinae, studying the violent mass loss that precedes their eventual demise as supernova. It can even analyze the chemical makeup of nebulas left behind by recent supernova and kilonovas, providing a detailed inventory of the elements created in these events and confirming our theories about the origin of gold and other rare Earth elements. In essence, the James Webb Space Telescope is acting as the universe's ultimate forensic scientist, collecting light that has been traveling for billions of years to piece together the history of cosmic violence. It is transforming our understanding of cosmic explosions from a collection of local, modern examples into a coherent narrative that stretches across the entire lifetime of the universe, from the first brilliant flash that ended the cosmic dark ages to the ongoing cycles of stellar death and rebirth that continue to shape our galaxy today. But the detection of gravitational waves, as monumental as it was with GW170817, has so far been like listening to the universe through a keyhole. Our current ground-based observatories like LIGO and Virgo are tuned to hear the high-frequency chirps of stellar mass black holes and neutron stars. To truly open our ears to the full symphony of the cosmos, we need to move beyond the limitations of Earth. The constant, subtle vibrations of our planet, the rumbling of trucks, even the crashing of ocean waves, all create a low-frequency hum that drowns out the deepest, most profound cosmic signals. This is where the future of gravitational wave astronomy truly begins, not on the ground, but in the pristine quiet of space. The next great leap is a mission called the Laser Interferometer Space Antenna, or LISA. Imagine taking the principle of LIGO with its laser beams traveling down multi-kilometer arms and scaling it up to a breathtaking degree. LISA will consist of 3 separate spacecraft flying in a vast triangular formation, trailing behind Earth in its orbit around the Sun. Each arm of this triangular interferometer will be 2.5 million kilometers long. That's a laser beam traveling a distance equivalent to 6 times the distance from the Earth to the Moon, just to measure the space between 2 points. The sheer scale of LISA is what will allow it to access a whole new register of the gravitational wave spectrum, the low-frequency band where the universe's true giants sing. Free from terrestrial noise and armed with arms millions of times longer than LIGO, LISA will be sensitive to waves with periods of hours or even minutes, compared to LIGO fractions of a second. This is the domain of the supermassive, The primary target for LISA will be the in-spiral and merger of supermassive black holes. These are the monsters that lurk at the centers of galaxies, with masses millions or even billions of times that of our Sun. When two galaxies collide, their central black holes eventually sink to the core of the new, merged galaxy and begin a slow gravitational dance. They can orbit each other for millions of years before finally coalescing. This final merger is the single most energetic explosion in the universe since the Big Bang itself, releasing more energy in a final burst of gravitational waves than all the starlight from every star in the observable universe combined. For a brief, unimaginable moment, the merger of two supermassive black holes would outshine the entire cosmos in gravitational radiation. LISA will be able to detect these events from the very edge of the observable universe, allowing us to witness the construction of the cosmic large-scale structure in real time, as galaxies build their central engines through a history of violent collisions. But the science doesn't stop there. LISA's exquisite sensitivity will also allow it to listen for the gravitational hum produced by millions of smaller binary systems within our own galaxy. It will create a dynamic map of all the white dwarf and neutron star binaries in the Milky Way, a continuous background chirping that will serve as the gravitational soundtrack to our galaxy. It could detect the final moments of a star being tidally disrupted by an intermediate mass black hole, a process that would create a unique, rising gravitational wave siren. Perhaps most tantalizingly, LISA might even capture the faint, primordial ripples from the inflationary epoch, the violent expansion that occurred a fraction of a second after the Big Bang. This would be a direct probe of the universe's birth, a signal from the very instant of creation. The launch of LISA, currently projected for the 2030-50s, will mark the beginning of a new era, not just for astronomy but for physics as a whole. It will transform gravitational wave science from a novel way of detecting cataclysms into a full-fledged tool for surveying the cosmos, for testing general relativity in the most extreme gravitational fields, and for listening to the background rumble of the universe itself. We will no longer be limited to the brief, loud chirps of stellar deaths. We will be able to hear the slow, majestic orbits of the universe's most massive objects, the gentle hum of our galaxy, and possibly even the echo of the Big Bang, opening a window onto the most energetic and fundamental processes that have shaped everything we see. All of these stellar cataclysms and galactic eruptions share a single, magnificent origin story, a foundational event against which every supernova and gamma ray burst pales in comparison. We have explored the death cries of stars and the collisions of galaxies, but to complete our journey, we must travel back to the very beginning, to the ultimate explosion that set the cosmic stage for everything that followed. This was not an explosion in space, but an explosion of space itself, the Big Bang. Every single atom, every law of physics, every iota of energy that powers the phenomena we've discussed was born from this singular, incomprehensible event approximately 13.8 billion years ago. The name itself can be a bit misleading, conjuring images of a traditional fireball erupting into a pre-existing void. The reality is far stranger and more profound. In the initial state, the entire observable universe was condensed into a point of infinite density and temperature, a singularity where the very concepts of space and time as we know them break down. Then, in a fraction of a second, an unimaginable expansion began, not like a bomb fragmenting in empty space, but like the very fabric of the cosmos stretching and cooling at a rate that defies all intuition. During the first fleeting moments of this inflation, the universe grew from smaller than a proton to the size of a grapefruit in a span of time so short it has no human analog. This rapid, exponential stretching smoothed out the cosmos, creating the remarkably uniform background upon which galaxies would later form. As this expansion continued, the universe cooled, allowing the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, to freeze out from their primordial unity, establishing the rulebook that would govern all future cosmic explosions. Within the first 3 minutes, the universe was still a seething soup of fundamental particles, far too hot for atoms to exist. Protons and neutrons danced in a blistering plasma, and it was during this brief, critical window that the first atomic nuclei were forged. In a process known as Big Bang nucleosynthesis, protons and neutrons collided and fused, creating the universe's first stocks of hydrogen, helium, and a tiny trace of lithium. This was the first and most widespread act of cosmic alchemy, setting the initial chemical composition of the cosmos. For hundreds of thousands of years, the universe remained an opaque, glowing fog, as light was constantly scattered by free electrons. Then, about 380,000 years after the Big Bang, a pivotal transition occurred. The expanding cosmos had cooled enough for electrons to be captured by atomic nuclei, forming the first stable neutral atoms. In that moment, the universe suddenly became transparent. The light that was finally released from that primordial plasma has been traveling ever since, stretched and cooled by the ongoing expansion of the universe into what we detect today as the cosmic microwave background radiation. This is the afterglow of the Big Bang, a fossil imprint on the entire sky that provides us with a baby picture of the cosmos, a snapshot of its structure and uniformity when it was just an infant. It is from the minute fluctuations in this background radiation that the first gravitational seeds emerged. Slightly denser regions imprinted in this ancient light began to pull in more matter through gravity, eventually growing over billions of years into the vast cosmic web of galaxies, clusters, and superclusters we observe today. Every single structure, from the smallest dwarf galaxy to the largest cluster, is a direct consequence of those initial ripples born from the Big Bang. This profound connection means that the supernova that forge heavy elements, the gamma ray bursts that announce the birth of black holes, and the kilonovae that sprinkle the cosmos with gold are all part of a chain of events that was set in motion at the beginning of time. The laws of physics that allow a star to fuse hydrogen, that dictate the Chandrasekhar limit for a white dwarf, and that channel energy into relativistic jets were all codified in that first explosive moment. The Big Bang was not just the first explosion, it was the event that defined what an explosion could even be in our universe. It provided the raw material, established the physical laws, and created the gravitational landscape necessary for all subsequent cosmic violence. The brilliant, fleeting flashes we have catalogued are simply later chapters in a single, continuous story that started with the expansion of space-time itself, an ultimate release of energy that set the cosmos ablaze with light and possibility, a creative destruction from which everything, including us, ultimately emerged. From the quiet death of a star like our Sun to the universe-shattering merger of supermassive black holes, we have journeyed across a truly breathtaking spectrum of cosmic violence. We have witnessed how the serene night sky is a grand illusion, masking a reality of continual catastrophe and rebirth on a scale that defies human imagination. These are not random acts of destruction, they are the fundamental engines of change in our universe. The brilliant flash of a supernova is not merely an end, it is a necessary act of cosmic recycling, scattering the elements forged in a star's heart across interstellar space, providing the raw materials for new stars, new planets, and ultimately for us. The collision of two neutron stars, a kilonova, is not just a spectacular light show. It is the universe's primary foundry, creating the gold in your jewelry and the uranium that powers nuclear reactors. Even the most terrifying explosions, like gamma-ray bursts that can sterilize entire galaxies, play a role in the grand scheme, signaling the birth of black holes and testing the laws of physics in the most extreme environments imaginable. Studying these events is far more than cataloging astronomical curiosities. It is a direct line to understanding our own existence. Every time we pinpoint the afterglow of a gamma ray burst or analyze the spectrum of a supernova, we are reading our own origin story. We are piecing together the sequence of cosmic enrichment that transformed a universe of pure hydrogen and helium into one capable of forming Earth and life. The calcium in your bones, the iron in your blood, and the oxygen you breathe were all created in the heart of a massive star that lived and died long before our sun was even a glimmer in a nebula. We are, in the most literal sense, the children of these cosmic explosions, built from the ashes of long-dead stars. This exploration also highlights the incredible progress of human curiosity. Just a century ago, we believed the Milky Way was the entire universe and had no concept of black holes or neutron stars. Today, we can detect the ripples in space-time from a collision that occurred 1 billion light-years away and use telescopes to see the infrared glow of the first stars. We have moved from merely observing the light of the heavens to listening to its gravitational soundtrack and feeling the impact of its most energetic particles. The journey is far from over. With new tools like the James Webb Space Telescope and the future LISA Observatory, we stand on the brink of discoveries we can scarcely imagine, ready to probe the era of the first stars and listen to the low-frequency hum of the cosmos itself. The universe is a dynamic, explosive, and ever-changing arena, and we are privileged to be living in a time when we can begin to comprehend its magnificent fury. Now we turn the question over to you. After this journey through the universe's most energetic explosions, which fact left you the most astonished? Was it the starquake on a magnetar that could be felt across the galaxy, the perfect standard candle of a Type I supernova that revealed dark energy, or the incredible revelation that a single kilonova can forge hundreds of Earth masses of gold? Share your thoughts in the comments below. We'd love to hear which cosmic cataclysm captured your imagination. If you enjoyed unraveling these mysteries with us, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the wonders of the cosmos. The universe is full of secrets, and together we will continue to uncover them.